So welcome to Robotics 2. As we discussed in today's class, we are going to continue the discussion on quadcopter, and we will try to look at how do you control the quadcopter, the theory part, and then I'm going to walk you through the MATLAB exercise where we are actually simulating the quadcopter. Quadcopter is an underactuated system. And what do I mean by underactuated? That a quadcopter has 6 degrees of freedom, but only you have 4 actuators. And again, the coordinate system that we studied in the case of fixed wing is the same coordinate system. The only thing I want you to understand is you have a relationship between the body rates and the inertial rates. Body rates are measured by the gyro, which is on the quadcopter. And then what happens is the inertial rates are determined using iterative approach. So for an example, initially, when the quadcopter is stationary, roll and pitch, they are determined from the accelerometer measurement, and then use this, they are used in this expression to propagate. And then what you do is every iteration, you can use a complementary filter or a Kalman filter to update and then find out the inertial rates. Inertial rates are integrated to find out the inertial angles. Now, something to understand, and since you have hands-on working experience with Mambo, the adjacent propellers are actually rotating counterclockwise. And then in the last class, we talked about the torque constant. Finally, we looked at the expression. And at the end, what we realized that the torque given by the propeller and the thrust given by the propeller is a square of the angular velocity. So finally, what we did is we derived this equation. Thrust in the x direction, thrust in the y direction is 0. We only have the thrust in the z direction, and that thrust in the z direction is a factor k multiplied by omega 1 square, omega 2 square, omega 3 square plus omega 4 square. And then you can actually make this system efficient using shrouds or coaxial system. We also looked at the torque, and torque is derived using the basic aerodynamics, wherein you have the drag force, you have the total torque, which is Tz, which is B omega square plus I omega dot. And then there are 3 important torque terms that you need to take into account. One is torque, yawing torque, the torque that yaws the quadcopter. The next term is pitch rolling torque, torque that rolls the quadcopter. And then the third one is the pitching torque, the torque that pitches the quadcopter. Then we started looking at the equations of motion. Equations of motion are applications of Newton's law in the translational coordinate system and the rotational coordinate system. Typically, Newton's law is applied in the inertial frame. So mx double dot is equal to the external forces. So we have the gravitational force, we have the thrust. Thrust is given by the prop. Props are attached to the body. So the thrust is given in the body frame. That thrust needs to be transferred to the inertial frame. So that's why you have IRB that will transfer the thrust in the body frame to inertial frame. And then you have the drag force, and this drag force is in inertial frame. So you have this equation, the translational equation of motion, that is in inertial frame. Next expression is Newton's law in the rotational coordinate system, and this equation is also called as the Euler's equation of motion. This is an equation for 3-dimensional dynamics. And believe it or not, these 2 equations are very, very important. No matter what is the dynamics, whatever the dynamics you are studying. If it's the dynamics of a rocket, dynamics of a quadcopter, dynamics of a tilt rotor, dynamics of a coaxial helicopter, dynamics of the regular helicopter, dynamics of some octocopter, hexcopter. At the end of the day, these two equations are going to remain the same. Kinematic equations are going to remain the same. All the frames are going to remain the same. Now understand this equation is again T is equal to I times alpha. But understand T is equal to I alpha, the equation that you studied in statics and dynamics course in your undergrad, or probably the statics course or finite element course in your grad, T is equal to I alpha is only valid at three locations. As long as the moment is about the fixed point, or the torque is about the fixed point, or the torque vector, the radius vector and the angular momentum vector is perpendicular to each other, and then basically T is equal to I alpha equation is applied at the principal axis. So again, if you look at this equation, you have I omega dot is equal to omega cross I omega is equal to tau. This is the Euler's equation for rotational dynamics. And what I'm going to do is, I'm going to take omega dot onto the left hand side. And when I take the omega dot on the left hand side, I get omega cross I omega term on the right hand side with a negative term, and I invert the inertial matrix. Now I'm going to consider the moment of inertia about the principal axis. A side note, after we discuss this, I'm gonna run through the MATLAB exercise. Remember few classes ago, I showed you that MATLAB exercise, and then we turned the knob, and then I showed you different aspects of quadcopter. So a big note. So the first knob is on the principal axis. So wherein you have a potato, where the axes are the principal axis, again the principal axis are non-principal axis. So please understand, when we have principal axis, we have moment of inertia terms only at the diagonal. Off diagonal terms are zero. What that means is inverting this matrix becomes super simple, and determinant, the cofactor divided by determinant, will actually give you the inverse. So you get this expression, and then you expand this further, and then what happens is, this is very important, you have omega cross I omega. So omega is a vector. I omega is also a vector. So omega is omega x, omega y, omega z. So omega x, omega y, omega z. That stands for omega. I omega is Ixx omega x, Iyy omega y, Izz omega z. And to solve this cross product, you need to find out, you need to expand this matrix, which is I omega y cross I omega y Izz omega z minus omega z omega y Iyy plus minus j omega x Izz omega z minus omega z Ixx omega x. The last term k multiplied by omega x multiplied by omega y Iyy minus Ixx omega x omega y. So you will have an expression with I, j, and k's. What does it indicate? Cross product is a vector product. Cross product is a vector product. Dot product is a scalar product, which means at the end of the day, you are going to have a term multiplied by I, another term multiplied by j, another term multiplied by k, that needs to be added to term which is multiplying I, multiplying j, multiplying k. Everyone understood this? And on the left hand side, you have omega x, omega dot xi, omega y dot j, omega z dot k. So this is a vector expression. Everyone understood this? So at the end of the day, what you have is you have a vector equation. Any questions here? Now the next part comes is we got these equations. We got these equations. Now how do we control it? So how do we control? So please understand, whether we consider thrust or whether we consider torque, they are proportional to the square of the angular velocity. So propeller angular velocity is omega, thrust is proportional to the angular velocity square, torque is proportional to the angular velocity square. Now what I'm going to do is, I'm going to treat vector x1 as vectors of position, which means x position, y position, z position. X2 is velocity, which is x dot, y dot, z dot. X3 is nothing but the roll, pitch, yaw. So basically roll, pitch, yaw. And x4 dot is the angular velocity, which is omega x dot, omega y dot, omega z dot. Now please understand, so I'm going to have a differential equation in x1, another differential equation in x2, another differential equation in x3, and another differential equation in x4 dot. So I'm going to rewrite these differential equations something like this. X1 dot is equal to x2. X2 dot is equal to, please understand, this equation is going to be 0, 0 minus g plus 1 divided by m r body inertial thrust in the body frame plus 1 over m f of d. So now I have the first equation, which is the derivative of positions is equal to velocity, and derivative of velocity, which is acceleration, is equal to the expression that we obtained here. So this equation is duplicated as equation here. Then I'm going to have an expression x3 dot is equal to this matrix inverse x4, and this matrix R is nothing but the matrix R that we derived here. And this needs a little bit of discussion here. Please understand. So I have this rotation matrix. I have PQR. These are the body rates, and I have the inertial rates. So basically, this rotation transformation R is coming here. So this will be equation, and the last equation, which is x4 dot, is equal to the equation that we have derived here. This is the equation that we have here. So see, this term goes here and this term goes here. So now what we have is, we have the this derivative of displacement is equal to velocity. Derivative of velocity, which is acceleration, is equal to forces divided by mass. So I have divided all the forces terms by mass. Third equation is I'm relating the role of pitch yaw, which is the inertial rates to x4. And I want you to understand. So here, this equation is something like T dot, theta dot, psi dot is equal to x4 is P Q R. Omega x dot, omega y dot, omega z dot is P, Q, and R. So are you with me that this equation that I'm showing here, this equation what I'm showing here is my equation number 3. Everyone understood this? So basically x3 dot, this is my x3 dot, x3 dot is equal to R inverse x4. Are you with me? X3 dot is equal to R inverse x4. And that x4 dot equation, x4 dot equation is this equation. This is P dot Q dot R dot, which is nothing but x4. So this equation comes over here. X4 dot, which is x3 is the roll pitch yaw, x3, and x4 is angular velocity. Roll pitch yaw and x4 is the angular velocity. So which is PQR, body angular velocity. So now I got these equations, and these equations are needed to come up with a control. Now in a quadcopter, so we are going to look at 2 control strategies. And why is this important? So everyone understood that there are these 12 equations. Yeah.
Yeah, like what kind of techniques are used to determine the R inverse in real-time computation?
Oh, R inverse, typically what they do is they expand the matrix. So you have a series expansion of matrix. So for an example, so finding out A inverse in real time is difficult. So what you do is you actually perform something called as a binomial expansion. So you use I minus or I plus A inverse, and then actually there is an expansion, just like binomial expansion, there is an expansion for inverse. And I don't remember that expression for on the top of my head, but you have an expression. Yeah.
Cayley-Hamilton theorem is more computation in this.
Cayley-Hamilton theorem, I have seen in the real life calculations, what they do is, okay, since in real life calculations, the A matrix is inverted a fraction of a second. So the terms are very, very small. So for convergence point of view, you can approximate that in some type of an expansion. So something like A square plus A cube, there is some term of some type of expansion is used, and that is truncated. And the reason for the A matrix, the terms in the A matrix themselves are quite small. That's why that is used. So they actually don't find the inverse in real time. Finding the inverse of a matrix is a very computationally intensive task. So what they do is they basically find out this inverse using some type of an approximation technique or some numerical linear algebra technique. But I'll give you the expansion later. I remember, I actually, as a matter of fact, I coded that expansion, but I don't remember the actual expansion now. Yeah.
And for finding the x values, is it just backward substitution, simple backward substitution, or is there anything different?
Find out which values.
X value, x dot, x3 dot.
Oh, you got a differential equation. You have to use Runge-Kutta or some type of a numerical integration scheme to integrate. So at the end of the day, what you have is you have four coupled differential equations that you have to solve numerically. So you will do a numerical integration on these values. Any other question? So next thing is how do you control? And this is very important. So first I'm going to talk about the easier control, which is proportional, derivative, control. Now, this is the crux of the quadcopter control, okay? So imagine on the quadcopter, you have a gyro, and gyro is giving you the body rates. So basically it is giving you the roll rate, pitch rate, yaw rate in the body axis. So basically you have a gyro that is giving you a roll rate, pitch rate, and yaw rate. And basically this is nothing but the measured values of error. So what I'm going to do is I'm going to use the equation tau is equal to I theta dot, and I'm going to use tau is equal to some type of controller term, which is u of t. So I'm going to assume my controller term, which is something like this. So a quick recap. I'm going to assume my torque in the roll direction, torque in the pitch direction, torque in the yaw direction is equal to some value I multiplied by some error term in roll. So Ixx and error in the roll term, Iyy error in the pitch term, and Izz error in the yaw term. Now what is this error? This error term I would define something like Kd phi dot, Kd phi dot plus Kp integral of phi dot dt. This term, just like this, it's gonna be defined Kd theta dot plus Kp theta dot dt, and this term will be defined as Kd psi dot plus Kp psi dot dt. Now let me explain what that means. At the end of the day, here is what I want to do. If my aircraft is in stable hover, I do not have to change the values of the torques. Do you agree with me? If my aircraft is in stable hover, which means my aircraft should not be tilting, my aircraft should not be pitching, my aircraft should not be rolling, it should not be yawing. If my aircraft is in stable hover, then I don't have to apply any torques. It's so my torque in the roll direction, torque in the pitch direction, torque in the yaw direction is going to be 0. Now I want you to understand the case is because of some disturbance, because of some air, because of some wind, because of some disturbance, the aircraft or the quadcopter rolls. Now, as soon as the quadcopter rolls, you are gonna have some type of a non-zero output from the gyro. Do you agree with me? Gyro is going to give you the angular velocity. It's not going to give you an angle. So, but clearly, your expectation is your angular velocity has to be zero, but you got a non-zero angular velocity. So what I'm going to do is I'm going to change the value of torque based on the error in the roll. An error in the roll is nothing but this controller term, which is KD multiplied by roll rate theta P dot plus KP integral of roll rate. So that is the roll angle. That's why if you can see here, this is the proportional gain, that is the derivative gain. Once again, I explain. We do not have a direct measurement of roll, pitch, and yaw angles. We have a gyroscope. Gyroscope is giving me the roll rate, pitch rate, and yaw rate. So whatever value I get from the gyroscope, I multiply that by KD because it's a rate. Whatever value I get from gyroscope, I integrate and multiply that by the gain Kp because that is the value of the angle. Everyone understood this? Yeah.
That means you have to go and set the initial position of all of those.
No, simply put, so here is what's going to happen. If your aircraft rolls, for stable hover, what should be the value of roll? 0. As soon as the gyro is going to measure a non-zero roll rate, this is what's going to happen. As soon as the gyro is going to measure a non-zero roll rate, you would apply some restoring torque about roll direction. Now the question is, how much of restoring torque would you apply depends upon the amount of disturbance and the rate of change of disturbance. Does it make sense? What does that mean? Basically, if the disturbance is fast, you apply the countering torque quickly. If the disturbance is slow, you apply the countering torque slowly. So that's what it means. Same thing if it is pitching. Now you have the pitching disturbance. So KD multiplied by the pitch rate, KP multiplied by the pitch angle, KD multiplied by the yaw rate, KP multiplied by the yaw. At the end of the day, what you have is you want to stabilize your quadcopter. If it is rolling, you want to prevent it from rolling. You need to go back to its original position, which means if it's rolling like this, you would apply a counterbalancing torque so that it goes back to its initial condition. But clearly, you will have to adjust the PD gains so that it doesn't oscillate back and forth. Everyone understood it? Same thing happens in roll. Yeah.
But 3 degree of 6 degree of freedom is a PD controller and 12 degree of freedom.
No. The problem here is, before we go any further, you have understand we have to stabilize the quadcopter in a roll direction, pitch direction, and yaw direction. So I need to apply the roll torque, pitch torque, and yaw torque. Everyone understood this? Now we have 4 motors, which means essentially I need to control the speed of 4 motors. That is the only thing I have control over. So entire quadcopter control is just controlling the speeds of the props. Everyone understood this? And there are 4 motors. In other words, I need from these stabilizing torque values, somehow I need to find out the PWMs for those motors that would stabilize. Everyone understood this? So let me be a little bit more specific, and that will give you an answer here. So this is one equation, and if you recollect from the motor dynamics, and we looked at this earlier, and if you look at from the motor dynamics, please note that these are the equations for torque. Torque in the yaw direction, torque in the roll direction, torque in the pitch direction. Everyone understood this? So what that means is, at the end of the day, this guy needs to be equated to Lk omega 1 square minus omega 3 square, Lk omega 2 square minus omega 4 square, and B omega 1 square minus omega 2 square plus omega 3 square minus omega 4 square. So at the end of the day, all said and done, I should be changing omega 1, omega 2, omega 3, omega 4 in such a way that I apply the appropriate torque, and these torque actually provide the stabilization in the roll direction, pitch direction, and yaw direction. Everyone understood this? But there is a problem here. Can somebody tell me the problem? How many unknowns are we trying to find out? Omega 1 square, omega 2 square, omega 3 square, and omega 4 square. And how many equations do we have? 3. So we cannot solve this unless we augment this with one more equation, which is the equation for thrust. T is equal to mg divided by cosine theta cosine phi is equal to k times omega 1 square, omega 2 square, omega 3 square plus omega 4 square. Which means for stability, the thrust that is provided by the prop should compensate for the weight of the air of the force. Now I have 4 equations and I have 4 unknowns. I can solve these and find out values of omega square in real time. Everyone understood this? That is the crux of the quadcopter dynamics. And to be honest with you, once you work out the math, you finally get a very nice expression for omega 1 square. And I would write this equation here. Omega 1 square is mg. And that's why they say the quadcopter is control is simple. Cosine theta cosine phi minus 2 times b e phi ixx plus e psi izz k times l divided by 4 b k l. Omega 2 square is equal to mg. So if you use MATLAB or Mathematica to solve these equations, it will give you this very nice expression: cosine theta cosine phi plus e psi izz divided by 4 times b minus e theta Iyy divided by 2 times k times l. Omega 3 square is equal to mg divided by 4k cosine theta cosine phi minus 2b Vixx plus E psi Izz KL divided by 4b KL and omega 4 square is equal to mg 4k cosine theta cosine phi plus E psi Izz 4b plus E theta Iyy by 2kl. Now, and this becomes so simple. Please understand, theta and psi values you find out either from the acceleration measures. You can use either a complementary filter or Kalman filter or just accelerometer measurement to find out the roll angle and the pitch angle. So roll and pitch are given by the sensors. Then this indicates what type of control law you want to use. Whether you want to use a PID control law, or you want to use the PD control law, or you want to use some other combination, that control law fits over here. Then in this entire expression, the only thing that you are changing is this. And then you can have that quadcopter do a stable hover. So basically, this is all there to it for a quadcopter control. Any questions? Everyone understood this? Now what I'm gonna do is, but there are some practical problems. The practical problem is when the quadcopter is flying, how do you stabilize and how do you change these 4 motor speeds very quickly? Because you may try to stabilize the quad in the pitch, but it may become unstable in the road. It may become unstable in yaw. So that's why what is going to happen is you run something as a real-time operating system. What is a real-time operating system? Real-time operating system is just like an operating system working on your computer. For example, when you are typing something in the MATLAB, the operating system understands that you are typing, that prompt is going onto the MATLAB, you are moving your mouse, and even though these actions are happening serially inside the operating system, to us, it looks like they are happening at the same time. So what does operating system do? It, the real-time operating system, makes sure that these task switching is done very quickly so that it doesn't happen like serially. For an example, if you use Arduino, even in a for loop, the task will happen serially. They will not happen parallelly, or there unless you add some type of interrupts. So what operating system will do? Operating system will, based on the roll pitch and yaw measurement, it will change or tweak these speed values, omega 1 square, omega 2, omega 3, omega 4, so quickly that at 100 hertz there will be changes. So quadcopter would fly in a stable mode. Everyone understood this? Now what I want to do is, I would like to show you the MATLAB so MATLAB mini drone modules. What I want you to do is, I want you to look at Parrot example, Parrot mini drone. So you can copy this, and I don't know if I'm sharing my whole screen, bear with me. And then go on to MATLAB prompt. and then run this. And you need MATLAB R22B to run these mini drone virtual labs. So paste, and then you run this. And mini drone virtual lab example will open. And this lab will include some reading activity. This lab will also include some hands-on activity. So what you need to do is, you need to go down and you need to select a module. So the first module is the basics. And then it will take you through this mini lab. What is the lab activity? Then watch the video, setting up the control problem. Then if you have, at this point, you should have done this on-ramp and Simulink. And then what you can do is, again, you don't have to turn it in, but you can actually send the orientation. And as you can see, the Parrot Mambo is X orientation. And then what you need to do is, you need to actually see B is the motor commands. So A is the controller, B is the drone, and C is the sensor. And then you have to watch this video. Then what you need to do is, you need to go to the second module, which talks about the control. It will open another virtual lab, which actually will walk you through what the control aspect of the drone. And then, so it will take some time. So there are, yeah. No, it's a sensor feedback. Yeah. So, and then it will open the lab, it basically, and it will actually walk you through this control example of the mini drone. So, and there are two activities. First is, you have to get the drone to hover, understand the model, and then use different PID gains. Now, in this lab, at this point, I'm assuming that you got your drone to hover. Yes or no? Okay. Since you got your drone to hover, I want you to try these different values of, where you will use the KP, where you will enter the KPK, experience here, and right, the controller block. To change these values and see how well or how bad the drone performs. Everyone understood this? That's all there to it. And then the other thing is, you can actually look at the Simulink data inspector, where you will see the data. And then if you really need some fresh up on the PID control, this is where you will do the PID control. The next lab is maneuver. And these labs are sort of important to get you to do the final assignment 8 or the project 8. So you would do the maneuvering. And here, what you will do is, you would understand the finite state machine. And then finally, you would have maneuver the drone in a square path. Now, please understand that the last assignment, I asked you to program the drone so that it can actually follow a particular path. Have you done it? Okay. So this gives you the theory behind that assignment. And then you can actually, you use the square maneuver chart, and then basically, if you don't know what a state flow is, you can actually look at what the state flow is. The last part is the perception. Is drone needs to know where drone is and what drone is doing. So that is the part. And you have run those Simulink scripts and they will show you this nice simulation on how it works. So this is exactly what the assignment that I asked you. That color-based thresholding, detect a yellow color box and hover the drone over the yellow box. Everyone understood this? Yeah.
Is it that we would like that to know the app simulator? Or what's for one where about going pull out the controller portion of it, running that run that to the part of
I didn't understand the question. So if you construct the path in the simulator, you program, if once you run the simulation, if you program that onto the Mambo, Mambo should be able to do it. It won't do accurately, but it will do close. And then what you will have to do is, you will have to go back and you have to tune two things. First, you have to check your PID gains, make sure PID gains are okay for the actual flight path. And then secondly, adjust your color thresholder app so that it's actually perfect. So you will have to do some tuning. And then if you go down this color-based thresholding, then load images, perception, and actually all these are given in these folders, okay? So please take a look at it. And once that is done, then what I want you to do is, last but not least, is I want you to go to, and I will spend some more time on this in the next class, is basically go on to VH 6 degree of freedom startup. Run this code. And then this actually the big code base opens. So here, what you do is you are gonna go to the sequence, and I will do this in the next class. So I would actually go to inertia, Euler, derivative, Cottonian, ODE, F and PQ, electrical motor control, linearized, full model, and finally you can do the code generation and deploy that on Mambo. So I would explain this in detail in next class. But before that, my suggestion to you is play with these virtual labs and get some practical experience in flying Mambos. And then you are welcome to bring your Mambos to the class on Thursday. And you are welcome to try those the drones in the lobby that we have. I mean, only one student can do it at one time, or we can go on to the technology center, motion capture lab, or we can go to the student union. I'm sorry, not student union, student activity center, and you can try flying drones. And if you have any questions, I would be happy to answer. So with that, I'm gonna stop here and answer any questions you may have. If you need a replacement Mambo, please stop by my office. I'll give you a replacement Mambo. But next class would be the class where we would wrap up our drone assignments. Next week, I would show you the demos of how to design the autopilot inside the MATLAB. And that way you will have full understanding of fixed wing and quadcopters. Thank you very much and have a good evening.